Hello everyone, and welcome to part 3 of the Rubik's Cube series, where I aim to solve every Rubik's Cube without using any outside sources. Today we're going to be looking at this cube, the Megaminx. It's a dodecagon or a D12 if you play Dungeons and Dragons, and let's see how I was able to solve this cube in 20 minutes. So I picked up this cube at the Portugal airport, and the first thing I did was I just solved the side the same way I do with every Rubik's Cube. And now I just solve the next layer. So now we have kind of the next layer down done. So now I'll move on to the layer below, and we can do it the exact same way. Okay, so now that all we have left is the last layer, we'll solve it the same way that we solved the 2x2 Rubik's Cube, which is by solving for position first and then solving for orientation. And after experimenting for a little while, I found basically two moves that allow me to change position. And I'll show you by using the top of the Rubik's Cube. So the first move, which I call G, is just the same move that I had from the 2x2 Rubik's Cube. So in order to easily notate what move G did, let's number the corners from 0 to 4. So we have corner 0, 1, 2, 3, and 4. So we can see that corner 0 is still in the exact correct position. So move G did not change corner 0. Meanwhile, corner 3, it's still in the correct position, but it's been rotated kind of two positions counterclockwise. And then these three corners 1, 2, and 4, they've all kind of rotated. So you can see that corner 1 went to the position of 4, 4 went to the position of 2, and then 2 went to the position of 1. And so we can write that as 1 for 2. And then we say that both 4 and 2, they didn't get rotated. They're still in the right orientation. But corner 1 got rotated 1 orientation counterclockwise. So now let's look at a different move, which I'll call H. So this move is just so now let's see what happens after we do move H. If we're saying that this is corner 0, then we can say that corner 2 over here was left untouched. And meanwhile, we can see that corners 0 and 3 swapped positions. And then corners 1 and 4 also swapped positions. So now looking at orientation, we can see that the corners that were originally 1 and 4, they both rotated by 1 orientation counterclockwise. And then the corner that was originally corner 0, it also rotated by 1 orientation. And then again we leave corner 2 and what was originally corner 3 untouched. They have the same orientation. And to remind us what each move looks like, I'm going to draw a little diagram. We have position 0 and position 3, which remained unchanged. and then we have positions 1, 1, 2, and 4, which do change. So I'm going to draw it like this to say that. For H, we can say that position 2 remains unchanged, positions 3 and 0 swap, positions 1 and 4 swap. So I'll draw it like that. Okay, so now can we prove that H and G are the only moves that we need? Because theoretically it could be possible that we get a configuration of the Rubik's Cube where we need a third move that we haven't come up with. So let's see what we can prove. So in my experiences, I always found that I only needed like a single move, either G or H, to get all the corners lined up correctly. But let's see if we can show that that's the case. First of all, we have 5 corners and they have 5 positions that they can be in, so we can say that we have 5 factorial possible permutations for the corners. And when we're thinking about changing position, we have G is 1, 4, 2, and H is 0, 3, 1, 4. And now let's count the number of swaps that we do. For H, it's pretty simple. We just swap 0 and 3, and we swap 1 and 4. So we have 2 swaps. For G, we have something that looks like this. So at first you might say that's 3 swaps, but actually what's happening is that we do 1 swap and we go to 1, 2, 4, and then we do a second swap and we get to 2, 1, 4, which is exactly what we're saying, is that at the end of our permutation, we will end up with 2 in the first place position, 1 in the second position, and 4 in the last position. So actually, if we can say that this also has 2 swaps. And so my theory is that we can only do an even number of swaps. So basically, any situation where we only have 1 swap, so you can imagine like a solved cube, except 2 of the corners are swapped. I'm going to say that's impossible. So I'm going to assume that we can just get rid of the 2, so that we only have this many permutations. And now I'm going to say that the 5, the way I'm gonna get rid of the 5 by. So what I'm gonna say is that if I have a permutation that looks like this, it's indistinguishable from one that looks like this, because you can just imagine rotating everything by 2 spaces counterclockwise, and then we would get that orientation we see there. And so since we can move so easily between those 2 on the cube, I'm going to say that we don't care about the 5 anymore. Okay, so now we have 4 times 3 gives us 12 different permutations. And if we're able to show that our 2 moves can allow us to move between all 12 or permutations, then that means that we don't need another move. Okay, so the most surefire way to know that we're hitting all 12 orientations is to write them all down. So we start with the solved state, and we apply our moves to see if we can get through all 12 different permutations. For H, we get 5 different permutations that can be reached by selecting each different corner as the one that remains unchanged. For G, we again have 5 different orientations from which we can do the move. But then we have 2 choices. We can either rotate the 3 positions clockwise, or we can rotate the 3 positions counterclockwise. So we have a total of 10 different moves we can do. But it turns out that these extra moves are actually redundant, so we actually only have 5. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is interesting. This is showing us that we have one permutation we actually can't reach in a single move from H and G. So what is this missing orientation? We can find the missing permutation by looking at what's missing. So we see that we only have that for all the permutations we have 3 of each number in the second position, but for 4s we only have 2, so it must be a 4 in the second position. And then if we look at the 2 4s, we have 0, 4, 1, and we have 0, 4, 2, so we must have 0, 4, 3. So now we have a choice between 0, 4, 3, 1, 2 and 0, 4, 3, 2, 1. And so now we know that we have 0, 4, 3, 2, 1 because it takes 2 swaps to get from that permutation to this permutation, and we're running on the assumption that doing one swap is impossible. And so now we have our missing permutation. So now let's take a look at what this means. So we have one state that's solved, and then we have 12 other states. We can get to 10 of the states by using the moves G and H. And the last state, let's call the unsolved state. It should be no different from our solved state, so it should also be able to get to 10 states. And so we have the structure where every state can get to every other state except for the state directly opposite it in the circle. And looking at the 2x2, when we're trying to get the positions on the last layer, we have this move that allows us to swap 2 sides. And if we were to make a graph out of that, we would have the same structure, which I find really interesting. Okay, so now that we know that we can solve for position in probably in one move and possibly requiring 2 moves, let's see if we can solve the last layer for position. So I can see that we can line up this corner to be in the correct position, and then also this corner to be in the correct position. And now we just need to rotate these 3 corners, and we can do that simply by using move G. So we know that move G changes the positions of corners 1, 4, 2, and 4. So what we'll do is we'll line up this corner to be corner 0, and so that will make this corner 1, this corner 2, and this corner 4. And then if we do move G, we should see them all rotate. And now we can see that everything is in the correct position. So now we need a move that changes orientation without changing position. So let's start with h squared. So h squared will leave 2 alone. 0 will rotate by 1 and become 3. And then 3 will become a 0. So 0 rotates by 1. Similarly, 3 goes to position 0 and then rotates by 1 and comes back to 3. And then 1 rotates by 1 and becomes a 4. And then rotates by 1 and becomes a 1. And then 4 rotates by 1 and becomes a 1, and rotates again to become a 4. So now let's look at h plus 1 squared. And so what I mean by this is that we just increment every number by 1, suggesting that we just rotated our start position by 1 space. Okay, so now what happens when we do h squared and then h plus 1 squared? So we can see that we change the orientation of 2 adjacent corners. Okay, so now that we have a move that changes the orientation of 2 adjacent corners, let's apply that to solve this Rubik's Cube. So first I'm going to get both of these corners to have the correct orientation. Okay, so now that we have 2 corners with the correct orientation, let's add this corner to the mix. Okay, so I did the move once and I actually got this corner, but let's do it again to get this corner. Okay, so now we have these 3 corners correct. We just need to rotate these 2 corners until they are correct. And we have a solved Rubik's Cube.